Gram-Schmidt process. Gram-Schmidt process is an algorithm for finding an orthogonal basis for any non-zero subspace in Rn. In other words, Gram-Schmidt process helps us to find orthogonal vectors once we have any. To understand the Gram-Schmidt process, let's go back to section 6.2, where we talk about orthogonal projection. So if we consider vector y to be projected orthogonally on vector u, so this is my vector y, and it's straight lines sliding down. This is my projection, we used to call it y hat. That vector is projected on vector u. Because they both lie in the same direction, the projection is the scalar of vector u, and that scalar is calculated this way using the dot product. So the projection is the vector that we're projecting, dot product with u dot product u, this is scalar, times the vector u. Now, if you remember, the vector, we used to write, we denote the vector z to be perpendicular vector, and then if we can see from geometry construction that y hat plus z is equal to y. So y is equal to y hat plus z. If we subtract y hat from that, we have z is equal y minus y hat. So this perpendicular vector z is my vector y minus the projection. We will use that in Gram-Schmidt process. All right, if we go back to, if we go to section 6.4, we can see that okay. If we go to section 6.4, we have theorem that Gram-Schmidt process, if you have given basis, so you have a linearly independent vector and that is span for a subspace W in Rn, we defined that first vector V1 is this first vector from the basis, V2 we define this way, V3 and so on. And those vectors, V1, V2, V3, are orthogonal vectors. So Gram-Schmidt process creates from a given set of vectors, creates orthogonal vectors. The only thing that we need to remember is that we have given linearly independent vectors, or in other words, bases. If you have bases are vectors that are linearly independent and that they span the subspace. So if we have linearly independent vectors or vectors that span a basis, we can create orthogonal bases. So the vectors V1 are orthogonal. So what's going, like, how do we get this? So first we have set of vectors V1 up to Vpen, x1 up to xp. We take first vector to be the same vector, and the vector V2 is the orthogonal vector to the projection. This is projection of vector V2 onto vector V1. So the situation looks like this. I have set of vectors x1, x2, x3. I can always place them at the same spot. So let me first I'm gonna consider two vectors, V1, V2. I'm sorry, x1, x2. And in that case, what I'm taking the first vector to be x1. So this is my x1. And then the second vector I'm projecting. So this is my V1 or x1. This one was my x1 vector. Now I have vector x2 that I am orthogonally projecting onto this vector x1. So what I'm taking, the second vector is gonna be this vector, this is gonna be my V2. So we can see that my V1 is the big vector, and now I created orthogonal vector. So this is my projection projection is right here. This is my projection. And to get this vector v2, we used to have the vector z, right? So this vector x2 is equal to my projection plus the vector v2, or used to be z, the vector we used to call it z. Now we call it v2. So v2 vector is equal to x2 minus projection. So that's what we have right here. x2 minus projection. This is my projection, right? v2 vector is equal to x2 minus projection. So that's how we create the orthogonal vectors. So in that case, I would have my v1 is my x1 is the big vector. And now I created orthogonal vector to this. Once I have those two vectors, I can place them at the same, oh, I'm sorry. I can place them at the same, I can always place them at the same vector. So then I have v1 and I already have v2. Then vector v3 is created orthogonal projection as well, except that now those two vectors, v1 and v2, those ones are projection, linear combination. So the third vector would be perpendicular to both of them, so it's kind of going out of this one. So I will show you. So what's going on for vector v3? I have those two vectors in one space, v1, v2. Somewhere was my v1. Here's or perpendicular, oh, I'm sorry. Perpendicular to this one is v2. Here is my vector v2. And now I'm creating vector z3 that's gonna be orthogonal to those two. So I'm finding the linear combination or orthogonal projection on those ones, and I'm projecting perpendicularly to that space. So in other words, this is v3. Maybe I should draw a better drawing. So this is my x3 is projected onto the W space that is spanned by those two vectors that were already orthogonal. So this is the projection v3. The 3 actually is not really a projection. Projection onto those two vectors would be those two. And this v3 is my perpendicular vectors, which is right here. That's the perpendicular vector. So in other words, z vector. And then we proceed in the same manner as is. So this is the Gram-Schmidt process. First vector is taken as is. Vector, second vector is v2 is projected onto vector v1, and we take perpendicular to this, we subtract. So this is the perpendicular vector v, the z vector. And that's how the Gram-Schmidt process is created. We proceed. All right, so now we have examples. So once we understand the formulae, then it's pretty straightforward to just plug it in the coordinates, right, the vectors. Use Gram-Schmidt process to produce an orthogonal basis to this one. Find the orthonormal basis for the subspace spanned by the given vectors. So we have given vectors v1, v2. So for my, I'm sorry, x1, x2, we're gonna label them x1, x2. Now my first vector v1 is my x1 vector. And now v2 vector, first I'm gonna calculate the projection and then I'm gonna subtract. So first I calculate this scalar, which is this one. It's x2 dot product v1 with v1 dot product v1. So this is my scalar c or alpha. And then my vector v2, my vector v2 is my x2. So this is x2 minus this is the scalar, I call it c1 v vector v1, which is nothing else but x1. This vector v1 is x1. So then I substitute and compute those two. So then that gives me already, or that gives me, I'm sorry, that gives me already two vectors. First, the given vector, what was v1, and this is v2. And we can check that those two vectors are orthogonal by calculating the dot product, right? This is my V1, this is my V2 vector. If I calculate V1 dot product V2, I would take this 3, 0, minus 1, transpose it, times this vector minus 1, 5, minus 3. And if I calculate this 3 times minus 1 is minus 3, 0 times 5 is 0, and minus 1 times minus 3 is plus 3. So this is 0. If the dot product is 0, that means the vectors are orthogonal. Okay, moving on. So now we have find orthogonal basis for the columns of the given matrix. I think we forgot to find it, I'm sorry, and I don't even have it. Find the orthonormal basis for the space spanned. So once we have orthogonal basis, the next thing what we need to do is to find orthonormal. So we would need to calculate the norm of those two. So this is my V, one more time V1. We would calculate the norm of V1, which is square root of 3 squared plus 0 squared plus minus 1 squared. And in that case, a square root of 9 plus 1 is square root of 10. So then the orthonormal vector would be rescaled, V1 divided by this stuff, right? Or normal vector, we would pretty much normalize them. And then the norm of V2 would be square root of minus 1 squared plus 5 squared plus minus 3 squared. And this case would be what? 1 plus 25 is 26 plus 9 is 34, if I didn't mess up the calculation. One plus 25 plus 9. Oh, I'm sorry, this is 35, right? 35, because this is 10. All right, so then orthonormal vector would be, we divide this vector by the norm, right? So we would have 1 over norm V1 times vector V1. This would be normalized vector. So it would be 1 over root 10 times my vector 3, 0, minus 1, which gives me 3 over root 10, and the 0 over root 10 is 0, and minus 1 over root 10. So this would be my one normalized vector, and the other vector would be 1 over norm 2 times vector norm 2, which is 1 over root of 35, times my second vector minus 1, 5, and minus 3. And in that case, I'm getting minus 1 over root 35, 5 over root 35, and minus 3 over root of 35. So those vectors, those two vectors are orthonormal. They are orthogonal, and normalized means length is 1. You can check that the length is indeed 1. Okay, now we can move on. Find an orthogonal basis for the column space of the given matrix. So this is the column space. We would need to check if they are linearly independent, but then we can normalize them. Not normalize, I'm sorry. We can find the orthogonal vectors. So we use the Gram-Schmidt process. The Gram-Schmidt process is first vector V1 is the same as my first vector. Then we find the orthogonal projection of vector V2 onto V1. So V2 dot product V1 with V1, V1. So then we put the we put the second vector x2 transpose times the vector x1 or v1 is right here, and v2, we pretty much square each coordinates, right? Minus 1 square root, 1 square root, minus 1, and 1 square root. So that's what we have right here. And then we calculate this. I got the scalar 2, if I didn't mess up the calculation. So then vector v2 is my x2 vector, which is right here, x2 vector, minus the projection. So 2, the scalar 2 times vector v1 or x1. And if you calculate, that's what I got to this vector. Then x3, we plug it into the formula, or in other words, is vector x3 minus x3 projected on x1 minus x3 projected on x2, or orthogonal basis on the v1 and v2. So if we substitute all of them, so this is my x3 vector, and then we have x3 v1, what we use it, over v1. So if I square all coordinates, I'm getting 1 plus 1, which is 4, times the vector, minus, now I have x3, which is my right here vector, dot product v2, and v2 square 1 square plus 1 square plus 1 square is 4. So that's why I have the 4 right here. So then we have the times the vector right here. So I calculate x3, I rewrite x3, I calculate this scalar is minus 1 times the vector v1 minus, and this would be 16 divided by 4 is negative 4 times the vector v2. So if we perform the calculation, this is the vector v3. And you can check that this forms the orthogonal basis. Each two vectors are orthogonal. We will move on. So now we have the orthogonal bases are used in QR factorization of a matrix A, which is widely used in computer algorithm for different computations. So what is QR factorization is like this. If A is an m by n matrix with linearly independent columns, then A can be factored as A equal to QR, where Q is m by n matrix whose columns are orthonormal bases of columns of A, and R is an n by n upper triangular invertible matrix with positive entries on its diagonal. So how we gonna compute the QR factorization? So Q is not a matrix whose columns are orthogonal and has length 1. In other words, normalized. So we call it orthonormal columns. And R is an n by n upper triangular matrix. So on the lower upper triangular, if you have matrix, right? So you're gonna have some entries right here, and all of them below the main diagonal are 0. That's why it's called upper triangular matrix R. All right, since columns of Q are orthonormal, then Q transpose Q is identity matrix. To understand this, I'm gonna show you. If I have matrix Q has orthonormal columns. So my matrix Q, let's say that matrix Q, maybe I'm gonna write it down Q. Right here is my matrix Q. Let's say that I have this, I'm gonna call it column Q1. This is my column Q2, and this is my column Q3. This is orthogonal and length is 1. What does that mean? Orthogonal means that the dot product of those two is 0. So Q1 dot product Q2 is 0. Q2 dot product Q3 is 0, and Q1 dot product Q3 is 0. That means orthogonal. But now orthonormal means that the length of each of them is 1. We remember that if we square both sides, the length is 1, so length square must also be 1. Q1 squared must also be 1. But Q1 squared is nothing else but Q1 dot product Q1. So that's what it means, okay? So this is my matrix right here. I have the matrix Q. If I put Q transpose, so transpose is I take the row, put it as, I take the column, put it as a row. So this is my Q transpose, Q1 transpose, first row. Then this is my second row. So this would be my column transpose. I call it Q2 transpose. And this is my third Q3 transpose. If I multiply Q transpose, so this is my matrix Q transpose, and this would be my matrix Q. If I multiply this, I'm getting row times column. Row times column, that would be my first entry right here, right? So I'm getting Q1 transpose times Q. But what is Q1 transpose times Q is nothing else but dot product. Q1 transpose times Q1 is my dot product. And dot product is equal to 1 because they are orthonormal. So this value is 1. And if I take Q1 transpose times Q2, this is my dot product of Q1 and Q2, this is a 0. So if I perform all of them like this, or because they are orthogonal, they would be 0. Only Q2 with Q2 would be 1, which is this entry right here. All of them would be 0, 0, 0, 1. That's why if we have orthonormal matrix that has orthonormal columns, always Q transpose Q, it's going to be equal to identity. Okay, moving on. But in that case, we're going to move on. So if we are convinced that for orthonormal matrix or matrix that has orthonormal columns, we have this situation, then if some matrix Q transpose Q is identity, we know that this is always, if you have Q inverse times Q is equal to identity, right? So for any matrix multiply, then if you have identity, we call it inverse. So this Q transpose is my inverse in that case for orthonormal matrices or matrix that has orthonormal columns. The inverse is nothing else but the transpose. So that's what it makes it more attractive. Inverse is very hard to calculate, and it takes lots of computational space for computers. But if inverse is transpose, it's very straightforward. All right. So if we are to have the matrix, if we are to have the if we are to write matrix A times Q times R as a product of Q times R, then I can apply the inverse of both sides to this equation. Then Q inverse Q would be identity matrix, which is transpose, which is identity matrix right here. But Q inverse is transpose. So I have this Q transpose A is going to be equal to my matrix R. And that is how we're going to calculate the matrix R. First, we're going to find the matrix Q. Then we transpose it, multiply times A, and we will obtain the QR factorization. Q for matrix, R is R. Factorization means product, right? Product of two matrices. That's why we call it QR factorization. All right, so in that case, we're gonna move on to the find QR factorization for this matrix. So to find the Q matrix is nothing else. We need to have matrix that has orthogonal columns, orthogonal. So we have a matrix. Now we need to find orthogonal columns. We could have checked that they are indeed. So to find orthogonal columns, we would apply Gram-Schmidt process. And once we have orthogonal columns, we can normalize them and we would have orthonormal columns. So to apply Gram-Schmidt process, how was it? We take the vector v1 to be the first column. Then we project x2 onto the vector v1, which is x1. And then we take not the projection, but we take the vector, subtract the vector, right? We take the vector z, or in that case, we subtract, right? So if you have vector, one more time, how the Gram-Schmidt process was. So this is my x1, which we gonna call it v1, then vector v2, this is my x2. We find the projection, right here is the projection, but I'm not taking projection, is not perpendicular to v1. I need to find this vector. So this gonna be my vector v2. So projection plus v2 is my x2. That in that case v2 is x2 minus projection. I can write it down. x2 is my projection plus v2. So v2 subtract projection is x2 minus projection. I'm repeating the Gram-Schmidt process. So this is my projection. So I have my x2 minus projection, x2 minus projection, right? So if you apply everything what I'm just saying, we have this x2 minus projection of x2 onto v1, which is x1. So if you substitute everything as it goes, so you have the x2 and x2 transpose times x1, and then you have the v1, which is 0 square plus 1 square plus 0 square, right? Which is 1, would be 0 square plus 1 square plus 1 square. That's what v1 dot product v1 is, and it gives me 1. So then you perform the calc times the vector v1, then you have x2, 1, 0, 0, minus, this turns out this whole scalar is 1, so minus this vector, then I'm receiving that vector, right? Then the v3 is calculated as x3 minus the projection on those two. So just substitute the calculations, x3 minus, I'm calculating this scalar. Now I have x3 dot product v1 and so on. I calculate the scalars. And if you perform the scale, first scalar is minus 2. This scalar is minus 1. So I have x3 minus x2 v1 minus v2 1 v1. So if you substitute to the vectors, that's what I'm obtaining, this vector. So now we have the vector v1, v2, and v3. And those three vectors are orthogonal. We would need to check the length. We can see that this length is 1, this length is 1, but this length is not 1. So we need to normalize it. I can show you how we would need to check the length now. So the length of v1 is square root of 0 square plus 1 square plus 0 square, and that this square root is equal to square root of 1, which is 1. So the v1 vector, this is my v1 vector, has length 1. Also, this vector, which is the v2 vector, also has length 1. But the v3 vector does not have length 1. If I check the v3 length, would be square root of 0 square plus 0 square plus 3 square. So the length is square root of 9, which is 3. So if the length is 3, we need to normalize it. So I would take 1 over norm 3 times the 3 vector. So this would be 1/3 times this vector 0, 0, 3. In that case, I have 0 times 1/3 times 0 is 0. 1/3 times 0 is 0. 1/3 times 3 is 3/3, which is 1. So this is my normalized V3 vector. Normalized V3 vector. And in that case, then I'm just putting the Q. So my Q matrix is my V1, V2, and V3, normalize V3. If my V1 did not have length 1, I would normalize the first vector, second vector, and then third vector. So this is my V1, V2, and V3 normalize. So this is my matrix Q. To find matrix R, we already said we need to take Q transpose times the matrix A. So Q transpose takes the row, put it as a column, take the row, put it as column 2, takes the row, put as column. It just happened, it's just by coincidence that this Q and Q transpose are the same. Sometimes it can be, but not always. And times matrix A, and then perform the calculation. So you would have row times column, which is 0 times 0 is 0, plus 1 times 1 is 1, plus 0. So this is the first entry. Then we would have row times column to get the second entry. We would have 0 plus 1 plus 0, that would be this entry. And then this entry number 2 would be first row times the third column, which would be 0 plus 2 plus 0, which is 2. And perform the matrix multiplication, so you would get this matrix R. So then we obtain this Q and R factorization. Q and R factorization. And indeed, you can notice that R is always upper triangular. Q can be square, but does not need to be square. Depends on the original matrix. Example B, we have this matrix. We need to find QR factorization. We use Gram-Schmidt process to find orthogonal bases first. Gram-Schmidt process only produces orthogonal bases. And this is the same example from previous class. So if you check previously what we did, but Gram-Schmidt process, take V1 is the first column, is X1. Now V2 is X2 and minus X2 projected on V1. So this is X2 dot product V1. So we take the second one, put as a transpose, times X1, times V1, which is my X1, over V1, which is square the coordinates of each and every one, and times the vector V2. So then we have X2, this is X2, not V2. This should be X2, of course, right? X2. X2 minus this coefficient V2. So I have X2 minus 2 times V1, and I plug it in and perform the calculation. So this is my X2 vector. So I have the first and now the second. Now I need to find the third vector. The third vector is X2 minus the projection of a third vector on X1, third vector on X2, and plug it into the formula, perform the calculation. First, I'm calculating the scalars. If I didn't mess up calculations, I have -1. Then the second one is -4 times the vectors. So then you have -1 times the vectors, V1, V2, and then X1, X3, and you subtract and then we have those vectors. So now we find on all three, so vector v1, v2, and v3. They are all orthogonal vectors, but matrix Q has orthonormal vectors, so the length needs to be 1. I need to rescale it, normalize it. So I'm finding the norm of the first vector, which is the length, square root of minus 1 square plus 1 square plus minus 1 square plus 1 square. It's square root of 4, which is 2. So then normalize it, we would take the vector divided by the length, or 1 over the length. So each and every coordinate is divided by 2. So we have minus 1/2, and 2. The same, we're doing exactly the same for vector v2. First, find the norm or the length. Find the length, which is square root of 4, which is 2. Then we divide each and every entry by the length. In other words, we're doing vector divided by the length. Or this is also exactly the same. This is also, I hope everyone can see, as 1 over norm v2 times the vector v2, right? So 1/2, you multiply each coordinates by 1/2. Okay, and then we're doing exactly the same for vector v3. So vector v3 is, we've calculated the norm or the length, which is square root of 16 is 4. So we divide each and every entry by 4. So minus 2/4 is negative 1/2. Minus 2/4 is negative 1/2, and so on. So then the Q matrix is the columns from normalized vectors. So this is the first vector, it has length 1, and it's orthogonal to those two. So this is the V2 normalized, and this is the V3. And to find R, we would take the transpose, Q transpose. So I take the first column and put it as a row. Then I take the second column, put it as a second row, and then I take the third column and put it as a third row. And we can see that this Q and Q transpose are not exactly the same because the last row is different, right? And we would multiply times matrix A, and we are getting the R, which is upper triangular matrix. Always you need to have zeros on the very bottom corner to have upper triangular. So then QR factorization is my Q matrix, and R, where R is given right here. Pause the video and perform the calculations just to get more familiar with the Gram-Schmidt factorization.